Hey everyone, my name is Bo. I'm here to talk today about exploring the final frontier of scaling. A little background on myself. I'm the technical co-founder at Polymer, where we're working on IBC connectivity across layer 2s. So rollups are the final frontier of scaling. And what do I mean by that? So Ethereum launched in 2015 under the code name Frontier. Since then, many layer 1s such as Solana and Monad have launched or been created to test the boundaries and scaling limits of L1s. L2s, on the other hand, represent a new frontier for scaling. Unburdened by layer 1 consensus, layer 2s can make trade-offs that aren't available at the L1 level, enabling novel use cases like real-time applications. Teams like MegaETH are currently exploring these layer 2 boundaries with 1 millisecond block times and over 100,000 TPS. Now, what do the scalability bottlenecks look like, and what are the differences between L1 scalability bottlenecks and L2 scalability bottlenecks? The internet today scales primarily on hardware. So a regular web server can take full advantage of hardware with maxed out specifications. Layer 1s, on the other hand, have fundamentally different scalability bottlenecks. At the consensus level, many consensus protocols require multiple rounds of communication for computers to agree on some execution results. This results in an upper bound on how fast a layer 1 can be. This bottleneck is represented by the problem of how hard is it for a large number of computers to agree on some result. At the network level, a round-trip packet between North America and Asia can take anywhere between 150 to 300 milliseconds. This, multiplied by the number of communication rounds required by a consensus protocol, places the minimum latency required for creating a block. Additionally, both transaction data and consensus messages also need to be gossiped through the network. And as L1 throughput increases and TPS increases, the amount of network bandwidth required by the protocol increases as well. And in general, outside of major data centers, network bandwidth limits are roughly max out at around 1 gigabyte per second. The network level bottleneck is captured by the problem of how hard is it for computers to communicate a large amount of data over large distances. At the hardware level, layer 2s are able to leverage their lack of blockchain consensus because they inherit various blockchain properties from their layer 1 to scale beyond these layer 1 bottlenecks and test the boundaries of what's possible at the hardware level and get performance that's very similar to that of a regular web server. And as you can see in the diagram above, we can see that there's two distinct scaling ranges where layer 1 scaling range is bottlenecked by consensus and network, and the layer 2 scaling range is bottlenecked by hardware. Now, what happens as layer 2 scale? Well, interoperability becomes the next bottleneck. To understand this better, I put together a little diagram here to show interop capacity. And you can see in the diagram that interop capacity consists of both verification capacity and data capacity. Verification capacity accounts for the overhead of the verification logic and protocol logic, examples of which include verifying a signature, verifying a zero-knowledge proof, checking for a DA proof, and so on. And an example of interop protocol logic can be anything between acknowledgements, timeouts, authentication, versioning, and upgrades. Data capacity, on the other hand, is the amount of proof or signature data required by the system. Example of which include a Merkle inclusion proof to prove an event log in a transaction header, or a signature proving the multi-sig verification scheme. And the interop cost is the amount of interop capacity that's utilized to achieve a certain level of security. So there's a direct relationship between interop cost and security. In this diagram, we model the interop cost from low to high, and we also model security from low to high as well. On the low end, we have a one-to-one multisig. A one-to-one multisig can be a single signature, which can range from anywhere between 48 and 65 bytes, the cost of which verifying on-chain could be roughly 4,000 gas, excluding base transaction costs. On the high end of cost and security, we can have things like proving layer 2 to layer 1 settlement. These settlement proofs can be much larger, at 9 kilobytes, and verifying a settlement proof is significantly more expensive at 800,000 gas. Now, what does this mean for interop at scale? Before we start, I want to do a quick primer on the different interoperability models in the market today. We have point-to-point models like Layer 0 and Hyperlane. We have hub-and-spoke models like Wormhole and Axelar. And now we have purpose-built rollup models like Polymer. So how does the point-to-point model scale? Sorry, were you taking a picture? Okay, yeah, no worries. So how does the point-to-point model scale? Point-to-point protocols scale extremely poorly in the number of connected chains, resulting in quadratic increase in interop costs as the number of chains grow. N-squared increase in verification costs, N-squared increase in data costs, causing many point-to-point protocols to opt for lower security mechanisms to improve performance. And we can see that in this diagram here. So in this diagram, we have two charts, one representing 10 connected layer 2s and one representing 1,000 connected layer 2s. This chart assumes all-to-all communication across these connected L2s at 30-second latency, which is the default configuration for a point-to-point protocol like Layer 0. We can see on the chart on the left that the lowest form of security, the one-of-one multisig, has a maintenance cost of roughly $2,000 per day. And this cost is calculated based on a one-on-one multisig having negligible off-chain verification costs, and the on-chain cost being potentially less than 30,000 gas, resulting in a cost of about 0.7 cents. However, as we look at the 1,000 connected L2s case, we can see that that $2,000 per day now becomes $20 million per day, which is significantly more expensive. A Lagrange state committee has different costs associated with it. A Lagrange state committee can cost maybe 15 cents off-chain for the generation of a zero-knowledge state committee proof, and roughly 250,000 gas on-chain for a total cost of roughly 21 cents. At 10 connected L2s, a Lagrange state committee solution can cost $60,000 per day, and at 1,000 connected L2s, a Lagrange state committee solution can cost over $600 million per day, which is quite expensive. Now, how do L1 hub and spoke models compare? Well, hub and spoke solutions generally scale better in the number of connected chains, or linear, or on the order of n. The main issue with layer 1 hubs is that they are layer 1s, which means that they are limited by the same scalability bottlenecks that layer 1s are limited by, which is hardware and network level bottlenecks. And when the layer 1 hub is used to connect different layer 2s, so especially the very scalable ones such as MegaETH, these layer 1 hubs then become the bottleneck. We have two diagrams here. We can see we have scalability on the left and we have latency on the right. And here we kind of visualize where the layer 1 hubs sit in terms of their scalability bottlenecks relative to the layer 2s that they connect. In the example on the left, we can see that if MegaETH is producing blocks at every millisecond and pushing over 100,000 TPS through their chain, and we have Axelar on the bottom there producing blocks every 6 seconds and pushing only a few thousand TPS through its chains, we can see that the L1 quickly becomes the choke point when it's dealing with these MegaETH-like L2s. We have Wormhole there at the network level bottleneck because Wormhole doesn't actually have an L1 chain. Their interop protocol flows through their Wormhole Guardian set, which doesn't have consensus, but is still limited by the network level bottleneck. And on the latency side, we can see that these L1 hubs are limited by Ethereum finality in terms of speed, which is roughly 12 to 16 minutes. Many of these layer 2s produce blocks much, much faster than that. So this is a major limiting factor for a lot of these layer 1 hubs. We can see with these diagrams that interop is quickly becoming the bottleneck. There hasn't been a lot of innovation in the interop space in the last few years, while in the L2 space, you have a lot of new teams exploring this new design space. And with this new design space requires new solutions on the interop side as well. So Polymer hyperscales interop capacity. And we do that by scaling both verification capacity and data capacity. Polymer scales verification capacity by creating dedicated L2 block space on Ethereum for interop, and Polymer scales data capacity by leveraging EigenDA to both increase data capacity and also optimize costs. And unlike general purpose built rollups, Polymer is a purpose-built rollup, meaning that we can make workload-specific optimizations that can further increase verification capacity and verification costs. For example, when paired with a Lagrange state committee solution, we don't need to generate a zero-knowledge state committee proof for every connected L2. Instead, we can stream raw attestations, raw state committee attestations directly to Polymer and generate a single ZK state committee proof for all connected L2s, resulting in an order of magnitude decrease in verification costs. Polymer also is able to scale alongside connected L2s, as it's an L2 itself. Its scalability ceiling is at the hardware level. Polymer is able to generate blocks much faster than its L1 counterparts and is able to push significantly more TPS through the chain as well. And the most notable thing is on the latency side. So Polymer is the first protocol to solve reorgs at the fundamental interop protocol level instead of offloading this risk to the application level. We're able to do so with a novel reorg protection protocol that we've implemented, and it's based on the L2 architecture that we have. This enables us to enable pretty much real-time communication or instant communication across these L2s in a safe way. Polymer also is able to offer up to 1,000x improvement in security costs when compared to point-to-point protocols, and also some cost savings when compared to L1 hubs, although primarily the advantages of Polymer there are from the perspective of scalability and latency. We can see some numbers here on the chart here. Point-to-point protocols, one a multi-sig at 1,000 with P2P protocols is going to cost 20 million. With Polymer, we can have a daily maintenance cost of $20,000. And once again, this is at 30-second latency with all-to-all communication. And it becomes extremely prevalent when you look at Lagrange state committee solution. We can do that for $172,000 a day, whereas with the point-to-point system, you're looking at over $604 million per day. So what does this all mean for builders and users? For builders, we can get a whole new design space for your applications. Real-time interoperability across connected layer 2s, near instant communication depending on the block time of the layer 2. You get cost-effective security. You're able to leverage unique security features like reorg protection and also choose between different security trade-offs. And you get infinite connectivity. Any chain connected to Polymer is connected to every current and future chain as well. And I think what this means for a lot of application builders or rollup builders on Ethereum is that you don't necessarily need to bootstrap DeFi every time. You don't need to have liquidity on your chain. You can focus on building a specific application and instead rely on an pre-existing DeFi ecosystem and be closely composable with that ecosystem and interoperable with that ecosystem, and allowing you to focus on product versus bootstrapping a whole ecosystem of applications that's outside of the realm of focus. Now, what does this mean for users? Users can experience Web3 at internet scale UX, meaning you can create real-time applications with seamless experiences. And you can imagine a world where you can have perhaps an Uber-like application on-chain, a real-time driver, rider, and marketplace. Having worked at Uber myself, in order to create this type of database, in order to maintain and populate this type of database in real time, it's requires a lot of hardware. It's very difficult to achieve at the L1 level, but relatively more attainable at the L2 level. So I could imagine that you would have shards of writer and driver state across different L2s. And you can coordinate across these to create this marketplace or public marketplace that others can leverage for building Uber Eats-like product on top or an Uber-like product on top. And if this is interesting to any builders, please reach out to me via DM on Twitter, and I'm happy to answer any questions.